So guys, it's focus. So the Cape Chemistry Unit 2 paper 2 for 2023. Let's begin. Number 1, give the IUPAC name for compound A whose molecule is shown below. What is the name?
As as 3 bromo pentane.
Pentane. Yeah.
3-bromopentane. Alright. So let me ask you a question now. Is it 3-bromopentane? Will I get a mark for that?
You
No.
need to
No,
like
Not necessary.
3-bromopentane.
Lovely. Alright. Moving on now. A hydrocarbon with a molecular formula of C6H14. What is that? Is that an alkene or alkene? C6H14.
out
Alkane.
Alkane.
Alkane, lovely.
yeah.
Is known to have 5 structural isomers. Draw the structures of each of these isomers. Alright. So let's draw some isomers. So let's see this now. That is 1, 2, 3, 4, 5, 6. Could we agree that it in its regular chain form is an isomer?
Yeah.
So that should count as an
Pardon?
isomer. Basically, the molecule in its regular chain form is an isomer, right? We can count that as an isomer, yes?
Yes, sir.
Chain.
Yeah, just it here like this in its chain form. Meaning in its regular form, this molecule is C6H14. This is an isomer, right?
Yes, sir.
Alright, so that's one down. Alright, next one now. Let's change it up a bit. Okay, is it okay if I stop
You
writing the
put
hydrogen?
in organza.
Go ahead. I was asking if it's okay if I don't draw the hydrogens because that's gonna take a lot of time. 1, 2, 3, 4.
Yes, sir.
Yes, sir.
Okay, we could have that. That is a nice one. Right? Let's go down. We could have something like this 1, 2, 3, 4, 5. We could have that as an isomer. Alright. We could have 1, 2, 3, 4. Okay, let me fix this. We could have something like this as an isomer. And last, is this last one? Yeah, and last but not least, we could have this as an isomer. These are the possibilities now. Those are 5 isomers that we could have. Go ahead.
Can you put on a ethyl group to make an isomer?
Yeah, you could put an ethyl group as well to make an isomer. Right, so remember there are multiple isomers now. Because they asked to draw 5 doesn't mean there's only 5. So you have multiple isomers that you can draw. Alright. Okay, so you just mix and match. All you do is just rearrange the atom them and then you look at other ones to see if they're the same thing. And if they're new, then it's an isomer. State the IUPAC names of 2 of the isomers that you've drawn above. So let's try this one. What's the name of this one right here? What's this? Go ahead.
Sir, 2,3-methyl. butane. 2,3 dimethyl butane.
Okay. Die.
Isn't it? Sir, I think it's methyl because we don't have two methyl groups on the same branch. Or I'm confused.
Alright, so first of all, we're gonna have a hyphen here and we're gonna change this to a comma. Alright. Okay, so our issue, okay, what's our issue with this now? Okay, let's go by the rules. The rules say we must identify the longest carbon chain. Right, the largest carbon chain, any direction you take it is going to be 4, right? 3, 4, right? We have that route there we could take. Or we could call this 1, 2, and then this would be 3. We could call this 4. So it could be anything. Alright, so notice that any way you take it, it's going to be 4, right? So what we're using, green or red?
Green.
Okay,
Green.
let's use green. Alright, lovely. So what are the substituents on green now? We have one methyl group here, and we have one methyl group here. So isn't it two methyl groups? One is on the second carbon, and then the other is on the third carbon. Therefore, it is 2,3-dimethyl butane. That's all. If it's not so, you tell me no. But I think it's so. Alright?
It is
Alright, so we have that.
So what are you saying? Sorry.
Oh, I was saying that if you don't think it's that way, then tell me if it's not that way.
No, sorry, I didn't hear what you said before that.
Okay, before about what specifically? I mean, you'd never heard, so you wouldn't know. Alright,
Sorry,
so go ahead.
you said the name of the compound, but I didn't hear. Is it that what it's on the screen there, or did you say something else?
No, it's on the screen. It's on the screen. It's the compound on the screen. 2,3-dimethyl butane.
Okay, good.
Lovely. And they're asking us to name one other one. So let's just name a random one. Let's name number 3. Let's name this right here. Name that. How would this be?
3-methyl pentane.
3-methyl
3-hyphen
pentane.
methyl pentane.
So 3-methyl pentane. Lovely. Moving on now. I want you guys to see the free marks that 2023 has on its paper. Alright, moving on now. See the free marks now. Let's look at these geometrical
That's
isomers.
bad though, sir, because usually they're like alternating difficulty.
Wow. Alright, so right there you put names for these geometrical isomers right here. What would it be? What would B be? Okay, I refer you open your mic, but it's really, I never heard you clearly. I heard you said trans something. So trans.
Transcend to in.
Alright, okay. So trans 2, 1, 2, 3, 4, 5, 10. Alright. And then C would be the same thing but cis, right?
Yes.
The thing is now you okay. At this level, people say you can't do this. Trans, pent, 2, in, right? But I personally do not prefer that way. But not because I don't prefer it doesn't mean it can't be possible, right? So you can write it that way. Alright? This is possible. Compound B reacts with hydrogen bromide to yield the Markovnikov product D as an equal mixture of two optical isomers. Define the term optical isomer. What is an optical isomer? Guys, what's an optical isomer?
Sir, an optical isomer is one which has it's two non-superimposable mirror images. Well, two enantiomers which are non-superimposable mirror images of each other that have chiral centers.
Okay. So these are chiral molecules. So we're looking at one optical isomer now, so it doesn't have to be in relation to something else. They're chiral molecules. So what else about them?
Sir, I think I would say that they have the ability to rotate a plane of polarized light. At least they're optically active compounds. I would say that.
Yeah, that are optically active. Optically active. Optically active. Right? So I would say their chiral molecules are optically active, right? The thing is, no. Define the term optical isomer. It tends to remember that the optical isomer itself, right? It could be an enantiomer or a diastereomer. So if you're gonna say that it's non-superimposable mirror images and stuff like that, that's only defining one kind of optical isomer. But in general, an optical isomer would be chiral molecules, right? That tend to have the same structure but differ, right, in their optical activity, right? So they're optically active chiral molecules. That's what I would generally call them to be, right? And to draw the structure of two optical isomers obtained in C2, is up here so? Oh, compound B is reacted with, okay, we're looking at the Markovnikov's product, right? It's D, right? But we're looking at the two isomers. That means that we're going to be looking at the Markovnikov and anti-Markovnikov product. So let's draw those. So what would they be? So have a go at drawing them real quick. Let me draw them as well. And then when I'm done, I'm going to present the answers onto the screen.
Sir, could you please repeat? I didn't hear you clearly.
We're going to be drawing the Markovnikov and the anti-Markovnikov product of B. That's what we're doing right now. Alright. So the bond breaks. It's gonna happen. Have you guys drawn your products before already? So is that going to have bromine on the second carbon or on the third carbon? right?
Sarah, really, can you go back to the image, please? One more time.
It's pentween. That's the molecule. All right. So let me start drawing now. All right. So we're gonna have two different things, right? So we can have something like this. That'd be 1, 2, 3, 4, 5. Or we can have 1, 2, 3, 4, 5. I'm drawing it out like this on in skeletal structure because I guess this is the way that how people look at it, right? We're gonna have a methyl group here. Okay, hold on. This thing is not allowing me to draw the things properly. I need to get back a surface bit. Alright, hold on. Let me disconnect my screen. Because I think the keyboard is touching when it's doing stuff. Alright, this is much better now. So that's one way, or we can have this way. So you guys can see what I'm doing.
Wait, sir, I'm kind of confused. Isn't it supposed to be like, aren't they supposed to be chiral? Or am I thinking about the wrong thing? Because
Both of them are chiral. Wait, hold on. Hold on. One of them is chiral. Two optical isomers obtained in C. Oh, I just saw what you're talking about. This is chiral, but that it. Hold on, let me look at the molecule one more time. Because that will give a chiral molecule and that will give a chiral molecule. So what's the issue here? Alright, so let's eliminate then. Let's eliminate and fix this issue. So first of all, this is chiral. That is chiral, right? The first one up there says chiral. Is it that I put the double bond in the wrong area? The other molecule doesn't see, you know. Oh, it will be chiral. No. It will be chiral. Go ahead. Somebody's raising their hand.
So for it to be chiral, does it need to be attached to four different things?
Yes.
I'm saying is attached to two carbons. This one carbon is attached to
Okay, give me one moment. Alright, so I'm gonna erase the molecule at the bottom. Okay. But that top molecule there, we can see that it's chiral, right?
no.
We can't see chirality. What's the issue?
I can't see why it's chiral.
Okay, let's look at this, right? So this is one group here. This is one group. This is a different group, and then this is a different group. Four separate groups. That's chiral.
Oh, so looking at the thing in its entirety.
Mm-hmm. So that's chiral, but they're asking us to provide another optical isomer. Pretty sure that this. Who will I get an optical isomer from this? Have you guys figured out how to get the next optical isomer from the other Markovnikov addition? Or from the other addition specifically? Because if we add, right, there is a double bond there. Alright, so what I'm saying is that the double bond exists on the second carbon, right? Of a pentane molecule, right? So what I'm saying is that why is this not selected? Give me one moment. Alright. Everything should be selected now. So what I'm saying is that we have a carbon here, double bond should be right there, carbon there, carbon there, carbon there. Alright. One, two, three, four, five. Alright. So something like this. If the double bond existed here, right? This is where the double bond is. Alright? That makes sense? So is the only way it could be a proper addition, right? Is if it was added here. Right? So it can be added here, right? Or it could be added here, but if it's added here, it's not chiral. Right? The only way in which it would be chiral is if we put it in a geometric position. Right? But it's not going to be geometric anymore because this is an alkane. Alkanes don't form geometric isomers. So that is my issue here. Did somebody find the other one already?
Sir, can I read back the question?
The question is
Can I read back
asking.
the question, please?
The question is asking us, right, to draw the structures of the two optical isomers obtained in C2, meaning that compound B undergoes Markovnikov addition, right? So not Markovnikov addition. It reacts with hydrogen bromide, right? So you're gonna have two different reactions, and the bromine and hydrogen will be added across the double bond. But what I'm saying here, in situation 1, the bromine will be here, and in situation 2, the bromine will be here. But in situation 2, when bromine is here, right, it is not going to be a chiral molecule. So am I missing something? Because that's not going to be chiral. Unless
Sir, if I had seen this question, I probably wouldn't have drawn it like this though, because the enantiomers where you have the thing coming out to the page and anything going into the page, I thought it would look something like that.
Okay,
I thought
so
all optical isomers would look like that.
all right, so we're okay. Let's draw it like that then, right? Because I'm thinking that I'm gonna have to do that to get an R and an S isomer. So let me do that then. Let's do that. All right. Let's quickly do that. So in that case, to draw it out like that now, because that's how I normally draw the molecules. Let's see if this is gonna work now. Right, for this molecule here, let's draw it like this. Right, so in this molecule, let's say that the hydrogen remains. That don't make no sense. Right, that's hurting my university knowledge. All right, so let's put the bromine up here. All right, and let's have, what's the mass of bromine again? 70. No, is that 80 something. The mass of the propanol group would be 3 times 12 plus the 7. That would be. Okay. Alright, so we're gonna have this now, the C3H7. Right? And here we're gonna have the methyl group CH3 and hydrogen. Right? So in this case, we can have two isomers from this, where we'll have that, right? Or we can have this. Okay, so this makes more sense now if I can do it freely like this. So if the bromine remains here now, and C3H7 is over here now, right? And then we'll have the CH3 over here and hydrogen here. Okay, so these are two isomers. Alright, so this can be, hopefully this makes sense to be the two isomers specifically. Wait, hold on. Yeah, these are not the same molecule. Alright, so these are mirror images of each other if you guys can see it. This should be CH3, right? This would be the, it's going clockwise. This is gonna be the R and this is gonna be the S isomer. Alright, so do you guys understand what was done to create these isomers?
Sir, why did you H3C turn into CH3?
Or because of the way it's oriented on the molecule. Meaning that if I have a bond, right, I won't write this here because it's making it look as if hydrogen is bonded to is on the double bond there. That doesn't make sense. So we always change how the thing looks. It's bonding to the carbon, so we bond it to the carbon and then everything else around it. So this is our isomer that we should get. Alright, so that makes sense. Just 2 marks, so it should be fine. So what's basically happening is that the Markovnikov product itself is optical and will warp 2 different isomers. Alright? It's now asking to state the color change observed in compound C when it reacts with bromine. So what would be the color change? What's gonna be the color change? Hello? What was that?
Sir, it's right?
Decolorizes, right? Right? So it will turn from the red brown to colorless. Alright, moving on. Name the functional groups highlighted. Whoa, this is so interesting. What's the functional group in A? What's functional group A in the A molecule there? What's that functional group? I want to hear other persons participating while I don't hear anybody else. Somebody else can tell me what this functional group is, please.
Alkene.
The alkene functional group. Alkene, right? What is B?
Hydroxyl.
Hydroxyl. Lovely. Right? What is happening in C? You know, what's the name of that? We don't have all day. So, what's the name of that functional group? Guys?
Carbon.
Okay. I'm okay.
Carbonel.
Okay, lovely, lovely. Taking too long, way too long to answer that. Alright, so identify the reagents 1 and 2 in the scheme above. So what's happening here? We have this compound, A, and it changes to B, then to C. So what's happening? What are the reagents? What's happening here? What's the reagent that will take A to B?
Bromine water.
It's going to be bromine. Lovely. Right? It's going to be bromine. Lovely. What will take B to C?
Potassium permanganate.
Potassium permanganate. Is it hot and acidified?
Acidified.
Right? We're talking about acidified potassium permanganate. Acidified potassium permanganate. Lovely. Moving on now. Identify the color change observed when compound A is converted to compound B. What happens when compound A is converted to compound B?
The bromine is decolorless, so it goes from red brown to colorless.
Wait, but is it? Hold on. It's the same bromine is decolorized? Because it add the bromine water. Oh my. Is it? That's interesting. Identify the color change observed from A is converted to B. Okay. That's interesting. Right. Based on your response in D2, what was the color observed for the conversion of compound B to C? What is the color observed there? From B to C, what happens there?
It goes from purple to colorless.
I'm not hearing. There's a lot of noise. What did you say?
Purple to colorless.
Purple to colorless. Lovely. Hopefully everybody else is understanding what's happening, because one person is just saying everything. So, where's the thing? It's not pink. Purple to colorless. Alright, we're just moving through then. Draw the structures of compound D and E in the spaces provided here. Why will we have to draw the structure of compound D and E? Is it that it's unknown? Oh yeah, it is unknown. Okay, so compound D, what would that be? What happening for compound D? Hello?
Sir, the chlorine group gonna replace the bromine group.
Are we so sure that's the reaction we're looking at? we so sure? Okay, so my idea, right, is that the sodium cyanide in hydrogen chloride solution, right, or an acidic environment, right, that is our nucleophilic addition reaction, right? Guys, hello, what is going?
Yeah.
Hmm? So if it is that, what we're looking at, we know that in our nucleophilic addition, right, we're going to end up with a hydroxyl group and a cyano group, right? A cyano group there, right? And then we're gonna have everything else remaining in the way it was before in CH3 here. I don't know why that click a 7. CH3 and everything else. Any issues with that?
Sorry, your screen came off.
It's not showing?
What is that? Okay, now I'm seeing properly.
The nucleophilic addition reactions, SN is a, well, is it a SN? No, I won't. It's not an SN2 or SN1. It's a nucleophilic addition, right? With carbonyl groups specifically to create um nitriles, right? Cyanonitriles, right? So it's a reaction that we've looked at in the reactions of. You guys would have to look at the reaction of carbonyl compounds. So I'm assuming that that's the reaction that they want us to look at for compound D. And then for compound E now, what they want is probably the Markovnikov product here of that reaction there. And if we write the Markovnikov product for that, it should have one hydrogen here. It should have two hydrogen here. It should have one hydrogen here. Therefore, the hydrogen will attach there. So, alright, so we're gonna end up with something like this. Right? So, hopefully the information making sense. It's not that bad. PR. So those are the two compounds, compound E, right, and compound D. Alright. Just two reactions, draw those compounds, and that would be fine there. Alright, so is that the end of module 1? No, it isn't. The reaction to form compound E, the reaction, that would be what? The compound E specifically, right, is just adding hydrogen bromide.
Electrophilic addition.
Electrophilic addition. You sure that's the name of the reaction? Is electrophilic addition the mechanism or the reaction?
Oh no, sorry, that was the mechanism.
It's a halogenation reaction, right? But the mechanism, I'm not gonna write mechanism, it's a halogenation. You could cite the halogenation of alkanes, right? It's a halogenation reaction. right? The mechanism is the electrophilic addition, all right? Give the reaction mechanisms. All right, now you're going to give the reaction mechanism here for the reaction that we looked at above, all right? Okay, so module 1, I think module 1, you guys say is a part of the issue. Module 1, module 2, because you guys have to go through all of these interesting things, all right? Okay, so let's have a look at this now. Compound A, give me a second, let me go back up to compound A because we need to be skipping through the paper to see the compounds that we're looking at. Alright, so what I'm gonna do, I'm gonna just take a picture of the compounds right now with my phone so I can just scroll back down and then do the question. Where are the markings gone? I did write on this thing. Why are the markings not here? Alright, oh there they are. So let me just take a picture and then scroll down and then we'll do the mechanism. Alright, so what we're doing here, we're gonna show the creation of our electrophile and everything. Right, 3 marks is just 3 marks for everything. Alright, so we have our hydrogen bromide. Is it right here? Okay, so let me erase this one. Okay, so we have our hydrogen bromide existing. Bromine is more electronegative than hydrogen. Therefore, we're going to have a slightly negative here, slightly positive. Right? So we have that there. Hopefully that makes sense. So if we look at our molecule specifically, we have OH here. It's a phenol. Right? And we're gonna have we're just basically drawing this of the molecule with that double bond there with our methyl group over here. CH3. Alright. So what's gonna happen here, we know that the electrons are gonna be attracting the hydrogen here, a full head arrow, and then we're gonna have electrons coming like this for bromine, and we're gonna get this now. Alright. So remember, what is Markovnikov's rule now? What is Markovnikov's rule again? Somebody restate it. What's Markovnikov's rule?
The more electronegative atom goes to the carbon, the least hydrogen.
I mean, okay, that's one interpretation of Markovnikov's rule. Alright, that's fine. Alright, but looking at this molecule, alright, we have to do it in order of how it would be done. So in this case, right, we're gonna have 2 different carbocations being produced, right? So what the one more unstable carbocation would be which position? Which position would be more unstable? Position 1 or position 2? Which would be more unstable?
Position 2.
Position 2 would be more unstable than position 1. Position 2 is a tertiary carbocation, you know, but position 1 is a secondary carbocation. So which one is more unstable?
Position 1.
Position 1 is more unstable, right? Need to remember that, right? And is position 1 the one that has least amount of hydrogens? Because technically here there would be 1 hydrogen here, right? 1, 2, 3, 4, and here there would be 1, 2, 3, 4. No hydrogens here. Therefore, the hydrogen will attach to this one, right? With the most amount of hydrogens, right? So we have that there, and we have the carbocation existing like this now. All right. So what we have now, right? Well, I mean, I would draw it. Should I draw it like that? Okay, let's draw it like this. So the bromine that's existing in the solution from before, right? Remember that it has free electrons now that it broke the bond. The electrons are gonna move from there towards that positive charge because we know that this is going to be some nucleophilic addition right here, and we're gonna end up getting this molecule. Right, so it's basically you have compound E, show how you got compound E. That's basically what they're asking. Alright, so this is me explaining how we get compound E. CH3 will be here, and our Br will be here. Everything is fine? Everything is fine, guys? Alright.
Yep.
Okay, lovely. Moving now to module 2, analytical methods on and separation techniques.